Think forward. Think Research Channel.
Change is coming to the Arctic as a warming climate alters a fragile landscape. Scientists are trying to understand this phenomenon and determine the impacts on a local and global scale. They are witnessing changes in the Arctic landscape that are provoking concern about the future, not just for the peoples of the North, but for all of the Earth's inhabitants.
Our program on Arctic transitions in the land atmosphere system, or ATLAS, is focused on understanding the interactions between the climate system and the land. In particular, we want to understand how changes in the ecology of the land surface are going to influence the climate system of the Arctic, and therefore the way in which the Arctic influences the climate system of the entire globe.
Changes occurring in the Arctic and neighboring subarctic regions may have major implications for the climate worldwide. The Arctic plays an important role in balancing global weather systems. The Earth's two poles act like ice packs on a feverish head, keeping the Earth's temperatures in check. As these areas warm, a delicate balance may be disrupted, leading to changes in global weather systems and climate patterns. One investigation has led them to identify a possible key character in the story of climatic change. One-celled creatures, or microbes, in the upper permafrost layers break down leaves and other organic material for food, creating carbon dioxide, or CO2 gas, in the process. As Arctic conditions change and the permafrost thaws, the microbes could produce more CO2, increasing the Earth's greenhouse gas levels. Recently, scientists discovered that these microbes were still active throughout the long Arctic winters, contributing to half of the annual Arctic discharge of carbon dioxide. Researcher Josh Schimmel is part of a team studying microbial processes in the northern soils. They're trying to understand how these processes change with the length and severity of the Arctic winter.
The Arctic really is about winter, as I see it. 9 months of the year, it's covered with snow, it's cold, and it's winter. And traditionally, biologists sort of forgot that entire period. When the last scientists left in the fall, they turned the lights out, the ecosystem shut down, and it didn't start up again until the first scientist arrived in the spring. And we've learned that that's really very, very much a wrong view.
The search for CO2 is concentrating on microbial activity within the upper layers of the permafrost. This frozen ground has several layers of soil, ranging from highly organic to mostly mineral. The upper layers freeze and thaw each year. Some of the toughest microbes live deep within these layers. Mineral properties in this soil allow them to live in sub-zero temperatures.
The permafrost people have known for a long time that even when the soils sort of bulk freeze, that there's still some unfrozen water on soil particles associated with organic matter in the soil, and that microorganisms can live in those water films. So presumably until those final water films freeze solid, they can remain active.
Researchers Gary Michelson and Chen Lu Ping are interested in how quickly microbes are decomposing organic plant matter as temperatures change.
But we can verify that at temperature below zero, in -2, -7 Celsius, we still detect the respiration from the soil. That means the bacteria still decompose in organic matter and produce gas.
As the soils are kept warmer by the insulating snow or increasing annual temperatures, these bacteria will become even more active.
That as you warm the soils by putting more snow on them, through this loop through the microbes, you change the availability of nutrients to plants. And this may have really big implications on how much plant growth there is, what plants grow. The more nutrients that are available, the more shrubs are likely to grow. The more shrubs that grow, the more snow you catch. The more snow you catch, the warmer the soils are, and you feed this feedback loop that could really change the whole nature of the tundra plant community and the tundra ecosystem.
Scientists are looking at several areas to see how the landscape and natural processes are interrelated. Through decomposition, microbes produce nutrients that the plants need. Snow provides insulation from the severe cold, keeping microbes active longer into the winter. As winter conditions change, the landscape becomes more suitable for the growth of shrubs and taller plants. These taller plants trap snow that warms the soil, encouraging more microbial activity and plant growth. This is called a positive feedback loop, one of several that scientists hope to better understand.
One of the things we've learned in the Atlas program is that the winter time is a crucial time for microbes. They're much more active during winter than we ever suspected before. And the factors that really determine this winter activity is the nature of the snow cover. So one of the things that we've had to do is to look much more carefully at the characteristics of this snow.
Researcher Matthew Sturm and his team are investigating the complex properties of snow in the Arctic.
We're always struggling to figure out how to measure the pieces of the landscape and the environment in a way that we could say that's a good representative measurement. We have to make our measurements at scales that are bigger than the elements we're in, the shrubs, the trees, certainly the dunes and the snow. If there's a shrub that's about this big and we make a microscopic measurement, we've measured just a small piece of the shrubs. Invariably, we can only really make spot measurements. But if we want to get a true measurement of that landscape, we've got to make a whole bunch of closely spaced spot measurements.
Dark shrubs absorb energy, making the winter landscape warmer. Areas with lighter surfaces, like snow, reflect much of the sun's radiated energy.
The thing that looks like a flying saucer is an albedo meter. It's an up and downward looking radiometer that measures how much radiation is coming down from the sun and how much is being reflected back from the earth.
Albedo is a measurement of the contrast between the dark vegetation and the reflective snow. Shrubs hold energy close to the earth. Areas with less exposed brush reflect more incoming energy. Snow reflects 4 times as much energy as shrubs, so if Arctic shrubs cover more of the landscape due to a warming climate, this will have a significant impact on albedo and the energy balance in the north.
Because once we know how much is going back to space, we've got to measure, well, how much white snow is there and how much other stuff.
Scientists are looking at another aspect of snow. It can be used as a weather record, showing how much snow has fallen and other properties related to temperature and water content.
We tend to think of the snow somehow as separate and independent from the plants and the ground, but in that environment, they're intermingled.
You gonna draw this or just take measurements?
I'm just going to actually dictate this one and try and draw it back at the house. Or you get about halfway down in the pit and you begin to hit woody material, the shrubs. That's one of the new areas we're starting to look at. What's going on there? When do the shrubs lay down? What are the mechanisms that let them lay down? What sort of survival mechanism is it for the shrubs? Just a bit more than a finger, but not just under pencil. Ice layers are all hard. And then what role do they play in determining the snow properties? And conversely, how's the snow interacting with them?
Researcher Julie Knudsen is taking snow core samples as part of a hydrology study. The goal is to establish a baseline for moisture content in the snow.
4 centimeters.
This information will help scientists predict changes to the landscape as climate warming alters snow depth and increases water content.
We take lots of samples of the snow because that determines the water content, which determines how much water there is available in spring runoff. And that spring runoff is the major hydrologic event of the year that reshapes the landscape through erosion.
Hydrological processes affect most natural systems in some way. Runoff during spring melt reshapes the landscape through erosion, allowing more and taller plants to grow. The thawing permafrost also contributes to this growth by releasing more nutrients from the soil. Hydrologist James McNamara is studying a landscape being transformed by increased erosion.
You can think of a watershed, the shape of a watershed, as an equilibrium landform. It adjusts its shape to spit out that water in the most efficient way.
Spring floods are a major reshaping force, but other, less obvious forces are also operating within the Arctic. Hydrologists Larry Hinsman and Doug Kane are researching how thawing soil and water movement impact the environment.
One of the objectives of our project is to determine the impact of climatic change on Arctic regions. Vast areas of the Arctic are underlain with ice-rich permafrost. And as the Arctic warms, that ice-rich permafrost can begin to thaw.
Erosion and the thawing permafrost are both at work transforming the landscape.
So if we get rid of the permafrost, you're essentially changing the geology. There's more of the soil column that's available for erosion. So with that change, even keeping the same amount of rain, we can expect the landscape to readjust itself until there's this new equilibrium landscape between rainfall and stream flow.
Researchers are measuring several rivers to determine how much water is flowing and how much material is being transported. Measuring these changes requires innovative approaches.
We have these chains with a drive point in the bottom, so we put these in the stream bed.
Researchers drive it in a couple feet deep. As the riverbed erodes to a lower level, more links in the chain will be exposed. The thawing permafrost and eroding riverbeds alter the landscape, cutting away at some areas and adding to others. This process alters the environment in a way that encourages increased plant growth.
We've moved our research from the tundra in northern Alaska to the Seward Peninsula at Council. This is the place where tundra is warming most rapidly, where permafrost is melting, and where we can look at the tundra in the process of transition to a forested landscape. As we go to a new area such as Council, we want to involve local residents. And so it's really important to work with the kids. They're excited about the biology, and they come out and work with us as part of our research team.
The changing Arctic landscape is already affecting the people who live there. Involving people from the community is an important component of the research program. It benefits the community and encourages a new generation of researchers. Village elders taught Cheryl Johnson about the plants and other traditional knowledge. Through the Atlas program, she's learning different perspectives on nature from scientists as they try to understand and label its elements.
I'm trying to find 95% of each species, and after I collect all my data and everything, I'll compare them to see which has the highest and least amount of vegetation or the area with all the species and stuff, comparing the biodiversity of all the sites and stuff like that.
Because of their involvement, these young research assistants now have a deeper commitment to understand global warming and to contribute to the search for answers. The Arctic is their home, not just a site for field studies. Local resident Chase Gray has spent much of his life exploring this landscape.
I kind of don't want things to change here in Council anymore because I love it just the way it is. Everything is just perfect here.
But if climate models are right, change is inevitable. And these changes are an immediate concern for those whose traditional life ways depend on the land and its wildlife. Scientists recognize that the lifestyles of the Arctic region are at stake. They hope their scientific studies might help local residents adapt to developing changes. Atmospheric scientist Jason Behringer is studying these transitions.
One thing about the transitions in vegetation is that we're likely to get a move from this tundra to a more shrub-like tundra. And we're likely to get a move from tundra, from shrubs to forest. And so these are probably the key transitions in terms of vegetation.
Researcher Catherine Kopass is classifying new plant growth and comparing it to the classic tundra.
Within this area in Council, we have 5 sites that truly go from a real low vegetation to a full forest. I look at the cover of the vegetation and the species composition. I look at how much biomass is in the sites by selecting random plots.
Is Mertensia leaf and Hylocomium.
Characterizing those plots very carefully.
And the Carex leaf is touching too.
After they've grown to their fullest during the course of the growing season, at what we call peak biomass, I harvest those same plots and sort them by their species and take them back to the lab and weigh them.
Kopass and her colleagues hope to see how increased shrub and tree growth affect the local climate.
The soil warms and potentially carbon is released. What I want to know is that potentially going to be balanced by the growth of the vegetation or not? And what will that mean for regional CO2 levels and for global CO2 levels?
Taller plants change the amount of light and heat that the landscape absorbs in both the summer and winter seasons. These changes can be identified by measuring the albedo.
In the tundra, around 20% of the incoming radiation is reflected, whereas in the forest, it's closer to 10%. So there's about 10% difference in albedo. And that primarily arises because of the complex architecture of the forest canopy here. The sun gets scattered and absorbed in the canopy, and so actually absorbs more of that radiation. And so then there's more energy then available to be partitioned into heating and moistening the atmosphere. And that's important because you then develop these contrasts between the forest and the tundra. And so if you imagine places at tree line where you have forest on one side and then tundra on the other, you get these large differences in heating between the two.
The warmer area of tall shrubs and trees contrast with the cooler tundra, creating air currents between the two environments. When this process is played out on a large scale, scientists speculate it could affect major weather systems.
The land surface has a very large impact on the climate system. We're trying to understand this at larger scales.
Gathering data from such a diverse landscape requires special instrumentation and a unique aircraft. This is a specially built Italian aircraft. It has been modified with sensors to measure carbon dioxide levels, temperature, and reflectivity. Researcher Walter Oshel has been measuring CO2 fluctuation levels across the northern Arctic.
With the ability to fly and measure flux, we can now sample over several hundred kilometers.
The data from stationary towers is compared with readings from the aircraft. If the tower and the aircraft agree, the aircraft data should be correct over long distances. If data from the tower and the aircraft match, researchers can assume the readings are accurate.
So this brings us into a new level of understanding and question where we can look at the controls by topography and vegetation type and changes in elevation, number of factors, and start correlating these with remotely sensed imagery from satellites. So we can start building towards a global understanding of Arctic behavior in response to climate variability.
The ATLAS program is expanding its focus. Scientists have been looking at specific sites on the ground to understand vegetation, hydrology, and soil properties undergoing changes. The towers record CO2 levels, albedo, and other information from a localized area. Aerial measurements provide information used to make broader generalizations about the Arctic. Data from specific areas on the ground and from the aircraft provide the information scientists will use to interpret satellite measurements. These studies will provide a circumpolar perspective of the Arctic. Another way to gain a large-scale view of the Arctic is through maps derived from measurements at specific sites on the ground in combination with satellite imagery. Plant ecologist Skip Walker and his staff use maps as an important tool to bring diverse kinds of information together.
One of the things we need to do in the studies that are part of the ATLAS project is to take information that's being collected in the field. Most of the work is being done at the plot level, where we're making fine-scale measurements of individual plants, the flux of trace gases from little plots of vegetation. A lot of the flux study happens at this scale, with investigators on the ground making measurements. The trick then is to translate this information that's being gained at this scale to landscape scales and to regional scales. This is the process of scaling up from the plots eventually to the circumpolar region. The suite of plants that grow on a specific piece of ground is a perfect integrator of the environment at that site. So if you look at a plant community in the field, you can tell a lot about the environment that community is growing in. If we map them, we get a very good picture of what the current environment in the Arctic is. And if we impose a scenario of change, we can predict how the vegetation will change across the Arctic.
The next step in these studies is to come to an understanding of how the Arctic works as a whole.
Scientists have studied the land, the atmosphere, and the oceans. Now they are putting the whole puzzle together, attempting to understand how these pieces fit together in the Arctic and Pan-Arctic, and how they interact with the rest of the global system. One thing has become increasingly clear. There is a remarkable interrelationship and interdependence between these natural systems. As scientists are studying how a warming climate is changing the Arctic landscape, they realize that these changes will not be limited to the Arctic, but will have global significance.
As we just saw in the documentary, trying to make sense of global climate change is a complex enterprise. On the other hand, if you talk to anybody from Washington, D.C. to Bethel, Alaska, they'll tell you current weather is crazier than ever. But what do we do about that scientifically? In the next half hour, we're going to meet 3 individuals who care passionately about Alaska, Arctic research, and human culture. Matthew Sturm sometimes gets ribbed by his colleagues, not because his work isn't impeccable, it is, but because he, a snow scientist, got published in a journal for biologists. But as we'll see, that's just one of the emerging properties as Arctic science comes of age.
I grew up on a steady diet of books about Roberts, Falcon Scott, and Amundsen, and Perry, and Cook, and all the polar explorers. And I even tried to get a fur suit when I was a kid. I thought that's what I needed most. So that's definitely what got me into it. Probably that and the fact I wasn't a good enough climber to make a living as a climber, so I thought, well, I better be a scientist.
Well, let me go to that for a minute, because I know you studied with Carl Benson, and in some way, your lineage as a researcher stretches back to some of the earlier explorers.
It does. Carl began his research after reading about Alfred Wegener, the continental drift person. And Wegener, most people don't realize, in addition to continental drift, was fascinated with Greenland and began a series of expeditions shortly after the turn of the century. Wegener died on one of these expeditions. And Carl read about this and had some questions about Greenland and began a series of epic traverses across Greenland. And I'm pretty sure that's what attracted me to Carl's work. So I'm a great-grandson, or maybe great-great academic grandson of Alfred Wegener's Greenland work. You know, sort of the mystique of the polar regions got us going.
But today, with high-tech stuff, it's not quite so individualistic. I mean, a lot of you guys are talking to each other.
Yes, it's changed dramatically. To be honest, if you go out today and the only thing you have to show when you came back was you had a great adventure, that's probably the last time you'll have any funding. You have to go out and come back with data, and solid data. And today that means interacting and working with a wide and diverse range of scientists, people doing many things. So we can't just work with other snow scientists anymore, or polar explorers. We've got to link up with a lot of different types of people to answer the questions that are pressing on us now.
So what is behind, what are the ideas behind this synthetic or synthesis that you guys are looking at?
Synthesis is a nice code word to say sort of understanding all the pieces back into the big picture of the whole. There's a man named Leffingwell who went up into the Arctic about 1900, lived on the Canning River in a cabin, driftwood cabin he built himself, spent several years, and he was interested in everything, the animals, the birds, the snow. He wrote papers on, some of the original papers on snow drifting. And when he was done, he wrote about the whole system. He synthesized within himself, just one individual. We're still interested in the whole system, but as science has become more and more specialized, no one person can do what Leffingwell did. We've got to move way beyond what he did. So one person might study the birds, another the tundra, the ice wedges, the snow, or the weather, and we've got to put it all together. And that's what synthesis is, putting all the pieces together, because we want to understand the whole thing, the whole Earth, or the polar regions of the Earth, not just individual pieces. So our code word, scientists use the code word synthesis. I think that just means to stitch everything back together and understand the big picture.
Yeah, but academically, it's led to some pretty interesting things. A snow scientist like yourself gets published in a journal mainly for biologists.
Yes, strange bedfellows maybe, and different vocabularies. So the first sort of step in that synthesis is you begin to talk to scientists doing something quite different from what you're doing, and you have to learn how to talk to them because they've developed their own vocabulary. But after a while, you discover you've got a piece of the puzzle and they have a piece. You know how satisfying it is when you're doing a puzzle with someone else and, wait, I need your piece. that's the sort of underlying feeling of the synthesis, and you find yourself doing that. And you often do feel a little bit out there like, what am I doing talking about something that I think I know almost nothing about? But in fact, by then you do know something about it because you've got all these other people you're working with who are experts in that other area. So, but it does, yeah, there's a few times when you think, what if they find out?
Well, and this leads me to, because, you know, I know ecologists like Terry Chapin and you and others have been looking at the land so closely and moving into areas like the Seward Peninsula, because that's where, in some ways, the real dynamics of a land system take place, right?
Yeah. I think our path, our research path in the LAI type research, it began by us saying, can we understand a relatively simple piece of the Arctic? We'll call it the tundra region. So we chose the Kuparuk Basin. And I think we did a good job there, but we recognized that we were looking at a pretty homogeneous piece. We took the easiest thing first. So the next step was to start to sort of expand that scope, get out to bigger pieces of the Arctic. And we quickly recognized that all the action was at where the transition zones were. As you went over the Brooks Range and got into shrub zones, as you went from tundra to trees or shrubs to trees, because those are analogs for how the Earth goes through changes, and that's where the most dynamic effects are. So our focus moved to looking at the places where we see landscape transitions, because the landscape transitions can also be thought of as how the surface might change in time. We're working still on that, but we quickly recognize the land and the sea are closely linked. So our views actually expanded beyond land. You talked about us, you know, doing strange things. We now have to talk to oceanographers, people looking at benthic organisms. So the focus has to go not only just to the transition zones where things are happening on land, but the transitions between the land and the sea, the transitions between the weather, the ocean, and the land. So the newer initiatives are all going to focus on trying to link these things together, because getting back to synthesis, we can't get a picture of the whole thing unless we take all the puzzle pieces and put them back into a picture of the whole thing.
Now, we've documented a lot of your work and that of your colleagues in attempting this synthesis, this putting together of the puzzle. But, you know, it strikes me that there's so much more work to be done. I'm wondering what you as a researcher are thinking, well, okay, we're going to have to incorporate the oceans, but then how do you link all of these together meaningfully?
That's a really good question. On an individual basis, a scientist like me sort of looks at what they can do personally. When they realize they've exceeded that, they say, well, who would I collaborate with? And looks for good people to collaborate, no different than any business venture. Who are the best people to find that synergy, that synthesis? At some level, then the synthesis becomes so complex, actually someone just takes that on as that's all they do. Someone like me who's a field researcher and can do a certain amount of synthesis might have to stop at some point, but someone else will go forward expressly doing synthesis. Their view would be, I'm going to take all the pieces I can find. So it's going to be a very dynamic process with surprising sort of alliances and unusual, you know, groupings of people, and people who begin to sort of focus specifically on synthesis. In fact, in the newest initiative that's coming up, it's called the Freshwater Initiative. The structure we've put in place, the organizers of that, is to have what we called a young Turk, someone who was really excited about doing nothing but synthesis and would do that rather than a specific piece of research. That would be their research. So I think that's how it's going to happen in the future, and maybe ever more so. You know, this process of sort of making alliances or specializing in synthesis, because we've got to get back to the whole puzzle, and that means putting all the disparate pieces back together.
Well, here's an interesting component, though. Unlike Amundsen and Wegener and Scott, whose exploits drew, you know, so the admiration of the general public, now a lot of politicians and policymakers are looking to your work to figure out what the heck's going on with global climate change.
Yeah, that's probably the big difference. We're not heroes. In fact, sometimes maybe we're the opposite. People want to know. They want to know what's happening, and people don't like answers like, well, maybe, or, well, it could be. People would rather have answers like, it is. And those are just about the hardest answers to give in science in general, and particularly when you're synthesizing a whole system. We can give answers more like, it appears to be moving in this direction. It is likely that this will happen. And we end up sort of clashing a little bit, because who wants to make economic decisions based on risk? The irony is, of course, we make economic decisions all the time with a risk factor, but I don't think we've quite worked out how to quantify the risk of our projections and how to transmit sort of our uncertainties to the politicians. So we still haven't quite dovetailed the science and the policy. It's an ongoing process. I know the president convened a large sort of summit meeting back in December, and aimed at just trying to figure out how to mesh those two. But I think scientists feel the pressure to produce more certain, or at least more results that you can quantify our level of uncertainty.
And I want to kind of branch off just briefly into philosophy, which is pretty dangerous territory to get to. But I mean, in one way, you can see how a politician wants to offer the public certainty and assurance, but philosophically, scientists aren't really looking for certainty. They seem to be looking for testable theories.
I think on a personal level, scientists would, just like the politician or the public, would like to know what's going to happen, but I don't think with a complicated system like the whole Arctic we can get there. So instead, what we have to do is construct models. They can be real models, numerical models that run on computers, or conceptual models of how it might function, and then test that. In testing it, we get a measure of the uncertainty. Did we come close to what actually happens? Did our predictions look like real predictions? So our focus, in a way, to get to to quantify how uncertain or how certain what we're telling people is going to happen is, we have to develop models and then compare them. And so our focus isn't really on the uncertainty, it's on seeing the performance. In a sense, you get to the same answer, but it just takes a lot longer. I think there's another thing, too, that plays into this, and that's that in science, we expect that what we learn today will be outmoded tomorrow. There's a certain expectation that it's a continually building process. We never quite get to that safe, secure ledge where we say, we're here and this is it. Yeah. We do establish specific facts, and those become, over time, clearly established. But there's an expectation that they'll look back in 10 or 20 years on what we're doing and say, oh, they were so naive. So armed with that kind of perspective, it's hard to go to the politician and say, this is going to happen, because we know we're probably going to be wrong, but we're going to have some of it right and some of it wrong. And that kind of, I think, differentiates how we think about things than a politician.
Well, I've been in meetings with you and your colleagues when there has been, let's say, very healthy debate over the data and what it means. And that seems to be part of science. While, a politician may say, well, they're disagreeing, but it seems like for you guys, it's okay to disagree.
Absolutely. Disagreement is the healthiest part of science, and I think there's a lot of misconceptions about how it works. Sometimes those misconceptions are actually even used to sort of discount the science when it shouldn't be. Here's, in my mind, how it works. Someone does a study and they bring a fact back. They've learned something, and they put it forward. We want a rigorous debate of whether they've established that right. The only way to really test that is for someone else to say, I question that. The person who established the fact expects that as well. They'll defend it. If they do a good job of defending it, someone else will then say, that makes sense, let me go test it, and they'll go try and take similar data. And if they get the same response, we build up a body of data. Pretty soon we've established this amount. Now there's lots more to establish. So someone goes out and gets the next piece that builds on it, and they bring it back, and the discord starts again. It's not really discord, it's the acid testing of the facts so that when we move on, the pieces we know we've established are established. So what you hear is the constant discussion about the newest facts. And it's easy then to say, oh, those guys don't agree, because you're not noticing that the pieces we've already established are well established, and we've moved beyond those. So we're constantly moving this sort of discussion and discord, seeming discord with us. And I think sometimes people pretend that that means we don't agree, because we don't tend to discuss the things we've got good agreement on. Those are already established. We're moving beyond them. That's how that sort of works in my mind.
And it seems to me, you know, every scientist wants to get the brass ring, a new, powerful, explanatory theory that accounts for everything, you know. But in some ways, science is the glory of losing or making mistakes or getting it wrong.
There are two parts to that are interesting. The first is every scientist is sure he's got the brass ring because they're focused, you know. The second part is we all say that you have to make mistakes, but I think no different than anywhere else. It's a terrible feeling when you do make the mistakes. It's a little more forgiving, I suppose, than sports. Maybe not. I mean, we expect, you know, the sports figures will have bad days, bad games, and for scientists the same. But there definitely is a cost of making mistakes. Strangely, the personal cost. At the bigger picture, the guy who makes a mistake often leads someone to do another study that does get the breakthrough, gets the brass ring. So the mistakes are as much a constructive part of what we're doing. But nobody likes to go, oh, that paper of mine, yeah, ignore that. That was wrong. You know, that's not a good feeling.
Right, absolutely. Well, but it seems to me, does it seem to you, I guess I should ask, that science, especially this kind of global climate change science, is at a crossroads?
I think so. Yeah, I think there are a couple of characteristics of that crossroads. The first is what we've been talking about. We've been disciplinary, looking at our individual pieces, and we've known now for some years we have to put the pieces together. We've been working on that. Our institutional constructs were still disciplinary. We're slowly retooling those to actually have what would be synthetic, you know, constructs that favor synthesis. So there's no question that crossroads is here already. The second one is things seem to be changing, have changed dramatically, and the pressure to interact politically with the public, with the press, to get our message out is higher than it's ever been. I think we're feeling that pressure in the sense that we feel like we need to be giving answers with certainty factors, you know, in as well. And I don't think that's galvanizing people and also creating, you know, healthy but sometimes fairly intense discussion of what's our role as scientists. So that's the second part of the crossroads. You know, the third, and you know, sort of the natural part of it is things are changing. We know they're changing. It's a very tough and slow process to find out how they're changing. Can we jumpstart the process somehow? Can we get in front of it and get the answers quicker? And I think a lot of people are thinking about that and wishing we could, but right now, you know, it's not clear how we would do business different to get there. So those three sort of pieces, we're at a crossroads of some sort. You know, dramatic decisions are unlikely, but I think things will move in one direction or another in the near future, and we'll see sort of how we've changed direction at that point.
And it seems to me, finally, that you and your colleagues have been incorporating a human dimension into the equation as well, how humans interact with the environment, but also the environment's impact on humans.
Yes. For many reasons, it's clear that we can't be ivory tower scientists anymore. The old stereotype that you and I've laughed about, the different types of, stereotypes of scientists, but we live on Earth just like anybody else. If the climate changes and has adverse or beneficial impacts, it affects my family as well as yours. So then there's a natural feeling of wanting to connect. Institutionally now, there's much more support for connecting, and that means, and the answers we have mean something to people. It's not just some esoteric piece of physics I've learned. It's what might happen in your backyard as Earth changes, and all of those are moving us towards the human dimension. And the politics you've mentioned a couple times, exactly the same. There's strong reasons for us to integrate ourselves more into the systems we live in, the political systems, the decision-making systems, and to share our results too, because it's a real exciting time to be in science. So the heroic age is gone when people vicariously shared, these dangerous trips over the ice, but maybe we should be sharing, sort of the intellectual trips we're on, which are these intellectual effort to understand a very large system that has profound ramifications for all of us on Earth.
If scientists like Matthew Sturm are beginning to acknowledge the human dimension in their work, Patricia Cochran might say, well, it's about time. She heads up the Alaska Native Science Commission, and as you'll hear, she says even science funders are beginning to acknowledge the holistic insight of Alaska's first people.
One of the important things that we know in Western science is that you have to validate everything. You have to be able to prove and to show over, put it into a polite little box that fits within a certain discipline. Very different from the way that our communities really look at things very holistically, where everything is connected and you really can't disassociate the air from the land, from the water, from the people, from the animals, from all of those things that are part of one universe. So it's a different way of looking at the world, and we're trying our best to put that information together in a way that Western science sees the relationship and our Native community information is validated. We're not just anecdotal information when you have 2,000 people telling you exactly the same thing. So that's part of what we're trying to do, is to help document the information and the reliability, the validity of our wisdom and our traditional knowledge.
Are you seeing scientists accept this kind of responsibility to engage the locals and the residents in this enterprise that they're engaged in?
I think it started slowly, but I think that the momentum has really picked up over the last few years. The Science Commission has been in business now for quite a number of years, since '93 when we first started. So we have a little history of now working in communities as well as with researchers to show how these pieces of information fit together. And I think many scientists are really beginning to embrace the idea of furthering and expanding their knowledge of information. That includes the observations of the communities who really do see things far before the scientists are on top of it.
It seems to me that this almost requires a special cadre of educators that really are sensitive to Native values and culture, while at the same time aware that modern science principles can play a role in amplifying and working together with that historic knowledge.
Well, I think you're exactly right, and we're trying to build communities in both directions. One, so that we're training our own Native communities as researchers, our hunters as biosamplers. So they're out in the field as they're hunting, they're also collecting research data. Our young people, so that they can take that data, our elders who can provide information to the communities and to the researchers themselves. And then in terms of the Western part, training the Western scientists so that they understand how the comments from communities really do fit into the world of science.
Well, we're running out of time, but briefly, what are the future programs? Do you see that this kind of idea of the marriage between Western and native cultural understandings will grow more deeply?
Well, I think that a lot of the work that is being done now and in the future has a lot to do with Native communities. People have seen the value and recognized the importance of putting together Native and Western science. We have programs now that are funded by national organizations, scientific agencies that value traditional knowledge. You can get a grant now for a traditional knowledge project, whereas a few years ago that was unheard of. We have a whole new program called the Human Dimension of Arctic Research, so that people in all disciplines, in all fields of research, really are understanding that there are human beings as part of the Arctic system and that they really need to be considered in everything. And so those programs are coming along very nicely.
Terry Chapin has long championed the synergy between native ways of knowing and scientific principles. A respected ecologist, he's been working lately trying to extend Arctic research so that it's truly circumpolar.
People can't be scientists coming into an area and doing studies and leaving. It needs to be a collaborative effort with local peoples, and that requires not only local people becoming scientists, but perhaps more important, having the communities that we visit and interact with becoming more interested and engaged in science because of the way it helps inform them about their lives.
Yeah, and of course indigenous peoples stretch around the globe and around the Arctic. Do you see, when you go over to places like the Russian Far East or the Inuit of Canada, a common acceptance and embracing of this kind of exchange of information?
Well, every place there's individuals who respond differently to visitors that come in. So I don't think there's any universal pattern, and a lot of it's idiosyncratic. But one thing that was really interesting is taking Henry Titus from Alaska to Siberia with us last summer. And when he was there, he found it really interesting to interact with local people there and find out differences in the way they interact with their environment from the way in which he's been taught by his elders.
Well, that leads naturally into what's next. I mean, it seems every year you guys have been looking at a wider and wider perspective, and now researchers are embracing the entire Arctic and try to synthesize what's going on. Is that right?
That's right. So as we go to a broader perspective, and especially as we go to a longer time perspective, we need to think about how the changes in the Arctic are affecting people and how people in the Arctic respond similarly or differently, and how their responses in turn affect the Arctic. And so I think as we go to these longer time frames, it becomes increasingly crucial that we include local residents as part of the process of science and as part of the end users of science.
And it sort of empowers. I mean, obviously, if a species impacted, like we saw with caribou, or we can think of whales too as another critical species that is an important cultural aspect of these people's lives, that if the climate changes, these species are impacted and thus humans are impacted.
That's certainly true. And as humans are impacted and as they change their attitudes and practices about reindeer herding, about whaling and so forth, that influences the impact of those animals on their ecosystems. And so because of these links with human society, it's absolutely crucial that we understand those linkages if we're going to understand the natural system as well as their impacts on society.
I have to ask you, oftentimes I'm really impressed when I walk out with somebody who's, you know, a resident, has been a resident, I guess, for thousands of years, about what they see. Do any of these residents train you researchers to look in particular ways or observe certain plants or animals that you probably wouldn't consider otherwise?
Oh, absolutely. For example, once when we went out to our micrometeorological towers with Henry Titus, he was saying, oh, there was a bear here just less than half an hour ago. And he was looking at things that we would never have seen. And so it made us be more careful about how we went about doing our work there.
Yeah, I bet. That's a good point. Well, I guess also going to the community aspect of these things, will members of the councils or the regional governments try to in some way aid you in your work? Are you finding a welcome from the leaders of a community?
I think in general there is a welcoming attitude. In places there's a legacy of insensitivity by scientists to local communities that's left some degree of reticence. And so I think what's needed in the future is just a clear sense of collaboration between local residents and scientists that come as guests to work in their areas.
Finally, was this a hard transition for you, from a plant ecologist to now almost a cultural ambassador as you go into other regions?
No, it's fun. These people have so much to teach us, and it's so much fun talking to them about it.
A long-term vision and scrupulous research. Those are at least two of the elements we'll need if we're to live fruitfully on the Earth. As we've seen, there are people engaged on a daily basis trying to make sense of the great chain of life and nature, how we fit into it, and how we preserve it for the future. I'm your host, Robert Hannon. Thank you for joining me in these discussions. This program has been a production of KUAC, Alaska One, and funded in part by a grant from the United States Department of Agriculture.